Deep inside a data center, when a thermal sensor detects a fire, a physical relay snaps shut. At that exact millisecond, local safety systems seize control of the facility to mitigate the hazard. This physical response is governed by the iron law of integration. Enterprise dashboards provide operational context. They never hold life safety command authority. Listed local controls, like your fire alarm control panel, execute hazard mitigation based on hardwired logic. They act with absolute deterministic authority, completely independent of the wide area network. This isometric diagram outlines the three-layer architecture used to bridge deterministic operational technology with IT enterprise monitoring. Layer 1 is the physical edge and safety tier. This is a highly regulated, hardwired, and isolated zone where the fire alarm control panel executes its local logic. Layer 2 is the DMZ. This supervised boundary contains redundant gateways, firewalls, and time servers. It strictly controls what data is allowed to pass upward. Layer 3 is the glass. This is your enterprise layer for normalization and reporting. It consumes data to create dashboards, but it is physically prevented from originating safety commands. True integration isolates safety functions from enterprise cyber vulnerabilities while still maximizing operational visibility across the entire data center. Coordinating a response requires extensive physical edge equipment, including items like access IP network speakers and intercoms deployed across the facility floor. Simply counting physical edge devices gives an entirely inaccurate gauge of integration capacity. A regulated environment generates a massive amount of secondary data. This diagram outlines the multiplier effect. A single physical point in the facility actually requires multiple digital objects on your monitoring platform. That one physical device generates a physical state, mechanical feedback, network quality data, and an exact timestamp. Mathematically, a facility with 1,546 connected physical points actually demands at least 6,000 distinct platform objects to satisfy Tier 1 licensing requirements. To reduce software licensing fees, operators will sometimes suppress diagnostic health data from reaching the dashboards. Hiding diagnostic data strips away the audit trail. Without that data, life safety authorities cannot verify the integrity of the system during an investigation. Deep inside a server hall, an energy storage system thermal anomaly ignites. The physical sensors instantly trigger cross-zone logic at the local panel. The local panel initiates mitigation before the enterprise dashboard is even aware a fire exists. This process flow maps the two parallel tracks of data at confirmation. The red track takes absolute command, selecting fire modes and releasing fail-safe doors. Simultaneously, the blue track's enterprise systems become strictly subordinate, bookmarking camera feeds for responders. Sending a command is insufficient. The red track logic measures actual physical airflow to confirm the hardware executed the instruction. Up at the glass layer, operators watching the dashboard rely on a strict 1.50-second latency target for their screens to update with this unfolding reality. Integrated context always follows local physical action. Situational awareness must never bottleneck hazard mitigation. For the blue track to provide forensically useful information, every packet sent to the glass layer must carry absolute, unalterable context. Looking at the upper half of this graphic, a single data packet is broken apart. It clearly states the originating source, the alarm class, the active state, network quality, and a precise UTC timestamp. If a network switch fails, the gateway will drop packets and lose its connection to the fire alarm control panel. It's for network latency, forces a strict status change at exactly 17 seconds. By the 20-second mark, the operator dashboard must visibly degrade that specific data point, labeling it stale. Artificially freezing a disconnected data point and displaying it as normal creates a false sense of security. It gives first responders bad intelligence precisely when they need facts. Under normal conditions, a facility might generate 50 distinct events per second. A multi-system failure obliterates that baseline. A severe incident triggers a correlated burst of 1,200 events per second. Transmitting this instantly would crash the platforms. Instead, a 100,000 event gateway buffer catches the spike, executing a controlled replay to feed servers at a manageable 500 events per second. This network must also handle the extreme bandwidth demand of 160 high-resolution security cameras streaming data during that exact same critical window. Data center integration architecture is engineered and tested for the worst-case disaster threshold. The daily operational average is irrelevant. Consider the ultimate edge case. The clean agent countdown begins, and the enterprise-wide area network completely goes black. Because the safety boundary is entirely deterministic, the fire alarm control panel continues the countdown and successfully discharges the clean agent into the server hall. This graphic highlights the quarantine and recovery phase. Managing the physical aftermath of a release remotely presents extreme danger. Operators are physically barred from using a digital dashboard to reset an energy storage system thermal event or to abort a suppression sequence. Safe re-entry, ventilation, and re-energization require a named authority to physically clear the space on site. When digital networks fail, strict adherence to hardwired physical logic stands between containment and catastrophe. Once the network eventually recovers, operators must immediately manage chronological drift to re-establish an accurate forensic timeline. While a calculated chronological uncertainty of 1.182 seconds is mathematically tolerated, original source timestamps are preserved. The system never silently rewrites time records to cover gaps. This graphic displays the four-step chronological process required by the post-incident playbook to properly investigate and restore the facility. Step 1 requires freezing and exporting the raw source logs immediately before the buffer rolls over and overwrites the initial burst. Step 2 correlates recorded digital commands against actual physical reality on the data center floor, verifying that the hardware actually executed the logic. Finally, a named physical authority clears the hazard, allowing the separate systems to be restored in a strict pre-approved sequence. Data center integration synchronizes an irrefutable chain of evidence. It achieves total operational visibility without ever compromising the authority of life safety.